Hello, everyone. Let's look at 6.3 inverses of matrices. So to start this section, you really need to know what an identity matrix is. And it's stated as an uppercase I, as such right here. We can have a 2x2, a 3x3 matrix, or even higher. But for our purposes, we stay with the 2x2 and 3x3. It's going to have on a 2x2, the upper left to the lower right diagonal will always be ones. Everything else is zeros. In a 3x3, same thing. Upper left to lower right, all ones, everything else is zeros. So when you're multiplying an identity matrix to any original matrix of whatever type it is, that original matrix never changes. So just like saying 2 times 1 is 2, 5 times 1 is 5, the original number does not change from its original. So let's look at how we're going to use an identity. First off, if you're looking for an inverse of a matrix, we can call a matrix any uppercase letter you want. I called it A here. When you multiply it with its inverse, and the notation is that uppercase A, same letter as its original, but with that little -1 as an exponent, results in an identity matrix. Sorry, that got cut off a little bit. Oh, we look at that, we take our original matrix, we multiply it with its inverse matrix, or vice versa, inverse matrix first, and then the matrix, you will get the identity matrix. Now, if you remember back with functions, we had inverse functions. F of x is the function, and f of -1 of x is its inverse. So before we had to verify if they were inverses as a function and use composites, put the g inside the f and then it come out as an x, and then switch places, the g first and the f of x second, and it would come out as an x. Well, we're doing the same thing with inverses. When we need to verify that two matrices are inverses, we need to multiply both ways. So AB and then BA. If both result in an identity matrix, then they are inverses. Just like our functions from before, f of x times g of x, we did it as a composite. We put the g inside the f and got x, and then we put the f inside g and got x, the variable of x. Now, this first example says to please prove that these are inverses. So we do multiplication, and I'm taking those two matrices. Remember, it's row times column, and whatever the result is goes in the position of row 1, column 1. So R1, C1 is right here. And after you do the math, which you learned how to multiply matrices at the beginning of this unit, you would get an identity matrix for the first one. Then going backwards, I got the same thing. I ended up with its identity matrix again. And because they both multiply out and are identities, then they are inverses. Now, how is this going to help in another situation? Well, let's look also on how to find an inverse of a matrix. So we have two different ways, or I shouldn't say two different ways, I apologize. Two types, a 2x2 and a 3x3. Now the 2x2 is actually the quickest one. Is if you're given a matrix, each number in that matrix has a actual location, and it's done by lowercase alphabet. So it goes on the row AB, and then the next row goes CD. Well, to find the inverse, what we would do is we put 1 over the diagonals subtracted. So we always start in the upper left and go down diagonal. So A times D minus C C times B, the up diagonal. And then we times that to, I call it the switch and flip. So down diagonal switches places, the D becomes the upper, and then the up diagonal flips signs. So whatever sign C was, it's now the opposite of what it is. Whatever sign B was, it's now the opposite. They don't switch places, they just switch signs. So we have switch and flip on the diagonals. Now, if when you're doing your multiplication, the AD minus BC becomes 0, well, 1 divided by 0 is undefined. That means that this matrix would have no inverse because you can't have an undefined item. Now let's do an example. So starting off, find the inverse of this 2 by 2 matrix. So I go 1 over downhill, 4 times 3 is 12, minus uphill, which gives me 10. Then I do the switch places and flip signs, reduce my fraction down, and then multiply it through. And the answer I get when it's finally multiplied is its inverse matrix. Now, what happens when we go to find the larger ones? It's slightly different than a 2 by 2.